In this lesson, you should be able to demonstrate the principles of plotting. Furthermore, you should be able to plot radar targets and calculate their course, speed, closest point of approach, time to closest point of approach, and aspect. And finally, you should be able to recognize what the effect of changing own ship's course or speed, or both, will have. Even though the introduction of ARPA has sometimes reduced the necessity for manual plotting, the actual plotting skill and a full understanding of how and why plotting is still very important is essential. The following pages are to ensure an understanding of the principles of plotting and to maintain competence in manual plotting techniques. The main purposes of plotting are to determine whether danger of collision exists and how close a target will pass off own ship and how much time remains before this will occur. The terms closest point of approach and time to closest point of approach are used to identify this data, and the terms are commonly abbreviated to CPA and TCPA respectively. Determine the course, speed and aspect of the other ships. Estimate the most favourable course of action to avoid a close quarter situation with other ships. There are many different methods for manual plotting. One can be as good as another. The important thing is to fully understand and feel competent and confident with the method used and the calculated results. Relative motion is the resultant motion of targets on the relative motion display, where own ship appears fixed, and the apparent target's motion is the combined effects of its own course and speed and the course and speed of own ship. Relative motion provides an immediate indication of collision risk, and if the trail is directly towards own ship, it is indicating that the bearing is not changing and a risk of collision exists. Relative course is defined as the target course relative to own ship, as deduced from a number of measurements of its range and bearing on the radar, and expressed as a heading. The actual relative course is not as important as knowing the CPA and TCPA, which is related to this relative motion. Relative speed is defined as the target speed relative to own ship, as deduced from a number of measurements of its range and bearing on the radar and expressed as a speed in knots. A ship which is abeam and travelling on the same course and speed as own ship will remain in the same position continually and have a relative speed of 0 knots. It is important to fully understand the meaning of the target's aspect. It can be defined as the angle between target ship's heading and its bearing to own ship, and normally referenced to the amount of side light visible, i.e. ship on the port bow has an aspect of red 40 degrees. Aspect is measured from dead ahead to 180 degrees on either side of the target ship. Heading is defined as the direction in which the bow of a ship is pointing, expressed as an angular distance from north. A relative bearing is a bearing taken with own ship's fore and aft line as reference, and normally expressed as red or green and a number of degrees. When in congested water, it can be useful to know where a ship is relative to own ship's head and where to look out of the wheelhouse windows. If the relative or true bearing of an approaching target remains the same over time, collision risk exists. A true bearing is a bearing taken with a gyro compass and with reference to geographic north. True bearings must be used for all position fixing onto a chart. Closest point of approach, or CPA, is defined as the shortest distance that will occur between own ship and a target. It is the perpendicular distance from own ship to the relative motion line. CPA must not be mixed with the point where a target crosses own ship's heading, often referred to as bow crossing position or point. BCP is the usual abbreviation for bow crossing position or point. Time to closest point of approach, or TCPA, is the time estimated as measured along the relative motion line from its present position to the closest point of approach. Click on the buttons to learn about the plotting triangle. The plotting triangle is the basis for all radar plotting. In this example, we will demonstrate how to create a plotting triangle step by step. It's common to use a plotting interval of 6 minutes, since this gives us a convenient scale for the speed vectors. For purposes of this example, our own ship's course is 0 degrees, her speed is 10 knots, and the radar is in relative mode. Start with drawing a vector in the center of the plotting sheet representing own ship's course and speed. On the radar, which, as previously mentioned, is in relative mode, we observe an echo in bearing 040 degrees at range 8 nautical miles. Plot the observation on the plotting sheet and call it O. Draw own ship's course and speed vector so that the vector ends in O and call its starting point W. The line joining W and O forms the first side in the plotting triangle and represents 6 minutes of own ship's motion. After 6 minutes, we make another observation. On the radar, the target echo is in bearing 020 degrees at range 6 nautical miles. Plot the observation on the plotting sheet and call it A. The target echo has moved from O to A in 6 minutes. This side of the triangle is the relative movement of the target and corresponds to the movement of the echo on the radar display. Join points O and A and extend the line beyond point A. Finally, we join points W and A. The direction represents the target's true course and the length represents the speed. We have now created a plotting triangle. When navigating in the vicinity of other ships, a watchkeeper must assess all other ships' movements and plan any necessary avoiding actions. The navigator must only take action after full appraisal of the situation, and not act on scanty information, and should take appropriate action to change the plotting triangle in such a way that he gets the desired CPA. The side OW, or way of own ship, is the only side the navigator can control directly by changing own ship's course or speed, or both. When the OW line is changed, the side OA will then change length or direction, or both. The only side the navigator cannot do anything about is WA, or way of another ship, which represents the other ship's true motion. It is essential to put arrows on the sides of the triangle to indicate directions. Remember that the arrows on the WO side and the WA side shall always be aimed away from W. On the OA side, the arrow shall aim from O to A, and is normally shown as an arrow with a circle round it. Click on the buttons to learn plotting can be achieved by various means. Modern ARPA radars do the plotting automatically, while older radars with cathode ray tube displays may have a special reflection plotter that can be placed on top of the PPI. Another possibility is to use special plotting sheets, or to use any sheet of paper. Plotting can be done with north up or head up on the paper, regardless of selected radar presentation. But it's always advantageous to plot north up and true bearings and ranges. In the following examples, the plotting is based on information from a relative motion display, though it could equally be true motion as only the range and bearing is taken from the radar display, and these will be the same on both displays. In this first example, plotting with head up will be explained. Own ship is stationary, so her speed is 0 knots, and her heading is 0 degrees. An echo is observed in bearing 040 degrees at range of 4 nautical miles. The position is identified as O. 6 minutes later, the same echo is observed in bearing 030 degrees at range of 3 nautical miles. The position is identified as A. In this example, we will calculate the target's course, speed, CPA and TCPA. The target's course and the relative course are the same since own ship is stopped and the OW line is nil. The target's course is obtained by parallel shifting the target course line through the plotting center and reading the course from the scale, in this case 246 degrees. The target speed is obtained by measuring the distance between O and A, which in this case is 1.5 nautical miles in 6 minutes, i.e. the target speed is 15 knots. The target CPA is obtained by measuring the distance from own ship to the closest point of the relative motion line, which is 1.6 nautical miles. The target's TCPA is obtained by measuring the distance from A to CPA, which is 2.5 nautical miles, which corresponds to 10 minutes. In this plotting example, own ship's head-up is used as reference, though this is not the easiest method. Let's use the following parameters for plotting. Own ship speed is 19 knots. Own ship's true course is 087 degrees. Time 0 minutes echo in relative bearing starboard 035 degrees, range 7.7 nautical miles. Time 06 minutes echo in relative bearing starboard 032 degrees, range 5.4 nautical miles. Normally, 3 ranges and bearings are taken to avoid the possibilities of errors. Plot the observations and call the first observation O and the last A. Draw the relative course line and extend this beyond the centre of the plot. The relative course line clearly shows that the relative bearing is gradually drawing ahead and that the range is decreasing. CPA will be 0.8 nautical miles to port. By marking off the relative distance, OA, on the projected relative track, you can estimate the target's position at 12 minutes, 18 minutes, and so on, and that TCPA is 20 minutes. Since CPA is small, plotting must continue until the situation is cleared. From O, draw own ship's reciprocal course, which in this example is 180 degrees, and mark the distance travelled by own ship in 6 minutes, i.e. 1.9 nautical miles from point O, and you get point W. Join points W and A, and for the purpose of this example, extend the line to point S. The target's true course equals own ship's true course plus the direction of WA on the plot or course. 087 degrees plus 278 degrees is 005 degrees. The target's true speed is section WA times 10, which is 15 knots. Let's use the previous example, where the target has a CPA of 0.8 nautical miles as the starting point for this example, where we will plan an avoiding action, and our aim is that the target should have a CPA of 2 nautical miles. Therefore, the point of contact of the extended OA line should be on the 2 nautical miles range ring. However, the plotting will take some time, so we plan for a change of course or speed to take place in a couple of minutes' time. We plan to make an alteration at time 09 minutes. Draw a line from point 09 to the 2 nautical miles range circle at point P1. This is the desired new relative course for the target. Draw a dashed line parallel to the new relative course for the target through point A and backwards. Take a pair of compasses and place the pivot leg at point W and the pencil leg at point O. Use the way of own ship line as radius and draw an arc from point O to the right. Mark the position where the arc intersects the dashed line and call this point X. Your new course is the direction from point W to point X. Therefore, change course to starboard to new course 117 degrees. If a change of speed is preferred as an alternative to turning to starboard, the new speed to achieve the same result can be deduced as shown on the plotting diagram. This assumes the alteration of speed takes place at 09 minutes and is immediately effective. A change in speed is represented by the segment labelled New Speed from point W to the new speed mark, normally identified as point O1. If your own speed from time 09 minutes is reduced to 11 knots, the target will pass with a CPA of 2 nautical miles on your port bow. A major disadvantage with head-up plotting is that since we plot starboard angles, the target echo will jump to a new position on the plot if your own ship changes course. This means that you have to start a completely new plot, and therefore this type of plotting is not recommended. The target echo jumps from point A1 to point A2 when you turn 030 degrees to starboard at time 09 minutes. When plotting north-up, true bearings are plotted and no calculation is required before these bearings can be marked on the plotting sheet. Though the type of plot can be different to the display in use, it should be remembered that the main advantages of using the stabilized radar display presentation is the change of own ship's course will not change target positions on the radar screen. More accurate true bearings can be taken, and the trails can be used to show useful information, and not just the yaw of own ship. The arrow on the graded circle indicates own ship's course, and the example is the same as used for head-up plotting. In relative motion, the centre of the plot is own ship. It stays stationary, and all bearings and ranges are measured from this fixed point. The relative motion line gives CPA immediately. A relative plot starts with the relative motion line and deduces the other ship's course and speed. True plotting has the advantage that it gives a natural and easily understood picture of the course of events. True plotting can be done directly onto a plain sheet of paper with a protractor or on the chart if the scale is large enough to give a clear picture. However, true plotting does not provide immediate CPA. Draw your ship's projected track on the paper or chart, and on that track mark the ship's position at regular intervals. Own ship's course is 010 degrees, and its speed is 8 knots. The following observations are made. Time 1 hour. Bearing 065, range 7.9 nautical miles. Time 1 hour 3 minutes, bearing 064.5, range 7.2 nautical miles. Time 1 hour 6 minutes, bearing 064, range 6.5 nautical miles. At time 1 hour, own ship's position is C, and at time 1 hour 6 minutes, the position is C1. Points W and A are then joined with a line to form a track. This track shows that the true course of the target was 285 degrees. The distance the target travelled in 6 minutes was 1.2 nautical miles, making its true speed 12 knots. To determine CPA, the plotting triangle must be completed to determine the relative track and the CPA. Dashed lines connect positions of both own ship and target at identical times. The necessity for plotting in reduced visibility and severely congested seas has created the need to provide a tool for automatic plotting. This required the creation of various plotting aids, and eventually the development of the Automatic Radar Plotting Aid, or ARPA for short. IMO has at last succeeded in making automatic radar plotting systems compulsory on all ships above 10,000 tons. This is a big step forward in making traffic observation by radar in reduced visibility much easier and safer. Heavy traffic can make manual plotting almost impossible, and the development of the ARPA has provided a much-needed method of automatic plotting and consequently safer navigation in congested waters. There are many possible sources of error in manual plotting. Here are the most important ones. Errors in plotted bearings and distances. Error in timing between plots. Error in the speed input. Errors in the radar compass heading. Manoeuvring of own ship. Unstable steering, yawing, and so on. Even small errors in one or several of these parameters can cause large and dangerous errors in the plot calculations. Always check these parameters as thoroughly as possible in order to reduce the possibilities for nasty surprises during manual plotting work. It is always worth remembering that on a relative plot, if the bearings and ranges are correct, the CPA and the TCPA are correct, even if errors in the OW line may create errors in the target information. The usual method of deciding whether a collision danger is present is by taking a series of bearings. If the bearing does not change, then risk of collision exists. This will still be the same on the radar as with visual bearings, and can be achieved by plotting and by just leaving the electronic bearing line on the target in question. However, the use of bearings is dependent on them being accurately taken and accurately plotted. In this example, an echo is wrongly plotted, bearing 030 degrees at range 8 nautical miles. The target's correct bearing is 030.5 degrees. The next echo bearing is erroneously observed to be 031 degrees at range 7 nautical miles. The correct bearing is now 030 degrees. The calculated CPA is 1.1 nautical miles to starboard and astern of own ship, but the correct CPA is only 0.4 nautical miles to port, with crossing just ahead of own ship. If this situation is allowed to develop, a very dangerous situation may soon occur. An error in distance measurement, as in bearing error, can produce grave results when judging the traffic situation. For example, an echo bearing is taken at 030 degrees at range 7.7 nautical miles, while the target's actual bearing is 030 degrees at range 8 nautical miles. The next bearing of the target is taken at 031 degrees at range 7 nautical miles, while actual range is now 6.9 nautical miles. The solid line through points V1 and V2 indicates the correct passing distance, which is a CPA of 0.4 nautical miles. The broken line through points P1 and P2 indicates the calculated passing distance, which indicates a CPA of 1.2 nautical miles. This type of error also shows the importance of having at least 3 bearings and ranges in a plot to show up any inaccuracies. To perform manual plotting quickly and accurately requires considerable practice, and with ARPA, the practical skill of plotting is reduced, while understanding the principles and limitations of plotting remain just as important as ever before in the history of radar. Other factors which may affect manual plotting and which can make manual plotting difficult: using an unstabilized display, maneuvering of own ship, extremely rough weather conditions. VHF communication is a way to make one's intentions clear to another ship and to arrive at an unambiguous decision about avoiding tactics. It can also be used for broadcasting a general information report to ships in the vicinity, particularly with ships using the AIS system. Such a report could state the time, position, course, speed, and maneuvers to be carried out. Though the use of VHF is widely employed in piloted waters, its use in open waters for collision avoidance is very limited and can be dangerous in reduced visibility, where there may be confusion about the identity of other ships in the vicinity. In the days of AIS, it is less dangerous, but should be used with great care. Only agree intended actions with ships whose identity is clearly established, and never totally rely on this agreed action, but continue to comply with the collision regulations.